is Rachel Doring, and here are my results and processes for Lab 4 on circuits. The purpose of the lab was to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuit, and finally, to examine the behavior of ohmic resistors and capacitors. The procedure of the lab was to use an online circuit simulation tool to create multiple different circuits utilizing multimeters, resistors, and capacitors. Some key concepts and physics principles that were used throughout the lab were energy conversion and the loop rule, which states that the sum of the potential difference in a complete loop is equal to 0, current conversion, and the node rule, which states that the current entering an intersection is equal to the current leaving that same intersection. And finally, Ohm's law, which is expressed through the simple equation delta V equals the current times the resistance. Here are my results for the first circuit of the lab. Using Ohm's law, I correctly predicted that the current was 0.02 amps. Currents I1 and I2, which are where each of the ammeters are located, are equal because there is no split junctions. And, when inserted backwards, the value of the ammeter does not change. Here, I replace one of the ammeters with a voltmeter to measure the potential difference across multiple different points of the circuits outlined in the bottom picture. On the left, I listed my results. The potential difference was measured to be 0 everywhere except across the places that there were resistors. So across A and B, which is across the battery, was -3 volts, and across C and D, which was across the 47 ohm resistor, was 0.959 volts, and across E and F, which was across the 100 ohm resistor, which measured to be 2.041 volts. Here is my graph outlining the voltage drops throughout the circuit. You can see that the sum of all potential differences is 0, which makes sense due to the loop rule. Also, the voltmeter, when attached to the circuit, has infinite resistance and therefore does not change the value of the ammeter. Below, I listed my results when solving for the resistance in each of the resistors given the voltage drop. You can see that the calculated values are slightly off from the listed values. This could be due to a small amount of resistance in the wires and battery that was not accounted for. For the next circuit, we attached a battery, a capacitor, and a light bulb in series. When the circuit is closed, the light is initially bright, but dims as the capacitor charges. The current of the circuit also decreases as the capacitor charges. When timed, it takes approximately 8 seconds to charge a 200 millifarad capacitor with a 9-volt battery and a 10 ohm light bulb. It takes the same capacitor approximately 9 seconds to discharge with the 10 ohm light bulb. When replacing the 10 ohm light bulb with a 20 ohm light bulb, while keeping the battery and capacitor the same, it takes about 15 seconds to charge the capacitor and about 16 seconds to discharge it using the 20 ohm light bulb. Here is a graph showing the relationship between the ln of delta V over V initial versus time. The graph shows the ln of delta V over V initial each second for 20 seconds. The slope of the graph is the -1 over RC, which can be used to find the RC value of the circuit. After some calculations, I found the RC value of this circuit to be 4.636. If this experiment had been done in real life and not in an online simulation, the results would have been slightly different as a real ammeter has a small amount of resistance that was not accounted for in the simulation experiment. If we conducted a similar experiment, only without the resistor, the simulation would charge the capacitor almost instantly. But, in real life, The wires and the battery each hold a small form of internal resistance that would result in the capacitor charging at a slower rate than predicted in the simulation.